intentionally the striking contrast between the modern bâtiment somehow the 530, yes, this is, yeah, and our academy, the library in Milano. Okay, so today I would like to continue to speak about superconducting fluctuations and Ginzburg-Landau formalism and beyond. About Ginzburg-Landau, we not finished. We arrived to the point when I will speak about fluctuations. So and I want to show you the very simple, exact solution for granules, for superconductivity in granules, which will be very informative. And then I will continue to three-dimensional case evaluation, so I will not solve it exactly. Then I will formulate Ginzburg-Landau criterion, time-dependent Ginzburg-Landau equation, and its application for description of the effect of fluctuations on the transport properties. And then the ideas of microscopic description of fluctuation phenomena and fluctuation spectroscopy. So actually, during our two questions and answers, we are a little bit prepared for this. You at least have a feeling how these calculations are performed. Okay, so why this? Yes. Okay. So in the BCS picture, you have the constant order parameter, but due to the presence of the thermal bath, or quantum fluctuations, there are always some fluctuations at the mean field picture. So what does mean to take into account fluctuation? This means to go with this or this those approximation beyond the mean field. How to do this? So we can start from the BCS Hamiltonian, and you see that BCS Hamiltonian has a fermionic and bosonic variables. So we know with you that if I know partition function, I know all thermodynamics. So I will write such partition function with the Barden-Cooper-Schrieffer-Hamiltonian. And then I will say there are fast variables and slow variables. There are fermionic and bosonic degrees of freedom. So I will integrate out all fermionic part, and I will leave only bosonic. So the role of electronic it forms me the coefficients of Ginzburg-Landau. I mean that we know with you that superconductivity is described by the Ginzburg-Landau function. And this functional contains coefficients alpha, b, and mass. So the statement is that these coefficients are formed by integration over fermionic part. And indeed, Garikov, in his paper of 58, demonstrates us the equivalence of BCF theory, microscopic theory, with Ginzburg-Landau close to TC, and gave us the values of these coefficients too. So I believe that if now I will use here the Ginzburg-Landau function, so the integration over fast variables, fermionic variables, form be A, B, and M. Okay, so but how to calculate this integral? It is not so simple, because in exponent, I have this gradient and force power. So I propose to start from the simplest case, so superconducting grain. So grain less than characteristic size of the change of order parameter. The close to TC, we know that the characteristic change of order parameter happens at the Xi-Ginsburg-Landau of T. So I will formulate later the criterion, but what I will do, I will omit gradient term, and my partition function for zero-dimensional case will be integral of, so my functional integral over order parameter, functional integral, now is reduced to simple two-dimensional integral over real and imaginary parts of psi, because psi is constant in granular. I believe that granular is so small that there is no room to change order parameter. So I have to perform integration over of exponent d2 psi of this exponent. This exponent has psi0 square and psi0 fourth. This integral can be expressed in terms of the f function, the probability function. And this is exact solution. This is exact solution beyond this partition function will give me immediately free energy minus T log C. And having free energy, I can calculate all what we want in thermodynamics. I can calculate heat capacity. And you know that in BCS theory, like in phase transition of the second order, there is a jump in heat capacity for 1.44 of the normal value. Here, look, this heat capacity, as I told you, take logarithm, calculate second derivative, and this is the shape of the heat capacity. Yes?
So what is the justification of using the Ginsburg-Landau theory in 0 dimensions?
Sorry?
You're talking about the thermodynamic limit and you're talking about 0 dimensions.
Okay. Like Vladimir Ilyich Lenin told, there are compromises and compromises. There is a zero dimensionality and there is zero dimensionality. The zero dimensionality in the sense of superconductivity, I told you. So this granula must be superconductor with size much less than Xi-Ginsburg-Landau of temperature. In order to consider this object thermodynamically existing, I need that it should have a huge number of degrees of freedom and interact with. So the psi is, for aluminium is 10 in power 4 of angstroms. So you can have huge amount of atoms and still will be zero-dimensional. From this is very important actual question always, for instance, about films. You have two-dimensional superconducting film. Does it mean that it must be atomic size? Of course not. It should be small in comparison with psi. So, so I want to stress that I get this jump characteristic for three-dimensional system, but smeared. And now tell me where is TC? The jump is smeared. So TC evidently moved. If we will decide that TC corresponds to this maximum, so this is moved down in comparison with bulk TC. So
this is for a small granule, the one on top?
This is for a small granule. And this is classical. So what I want to say, one can see that this function is analytical in temperature. Therefore, fluctuations remove phase transition in zero-dimensional system. There is no sharp transition. The smearing of the heat capacity jump takes place in the region of temperatures in the vicinity of T0, where X is order of 1. So epsilon critical, so where the fluctuation contribution becomes noticeable, essential, is this one directly from here. And I see that this is some coefficient, Tc over epsilon Fermi, and then psi 0 Q, so psi BCS, divided the volume of my particle. So I see that here starts the serious deviation from this picture. So if I want that my transition would be narrow, not smeared, so this epsilon critical should be small. That means that volume of the granula should be much more than 1 over density of states Tc. Or delta, I will call this value delta, must be much less than Tc. I rewrote the same. Look, I call delta the value mu v, density of states on the volume of my superconductor. And it must be much less than Tc. Look, this is very important. So the value delta is called spacing. And this is in finite size superconductor. This is the average space between the energy levels in my superconductor. So delta characterizes me the size of staircase in energy spectrum. And it must be much less than Tc. And Tc is delta.
This is Anderson criterion, right?
I come. So I won't say that considering this model, simple model, I see that my theory, when there is no smearing, so it corresponds to mean field. So I see that when delta is much less than Tc, the smearing of jump is small. So this means that mean field works. Mean field is BCS. So to apply BCS for finite size system, the spacing must be much less than delta. But remember, I will remember what was done in BCS. You integrated over continuous spectrum. You did not write sum over quantum states. You wrote integral of energy. So when spacing becomes of the order of delta of the scale of superconductivity, so you cannot believe more to BCS. So to go beyond superconductivity, BCS theory in zero-dimensional case means to take into account. So if you speak about superconductivity in granulas, indeed you have to perform summation of the letters of true letters. Please.
So in this case, so we like smoothen the transition. So you said we kind of killed the transition, but on the previous slide you said fluctuations remove the phase transition.
No, we took into account this is beyond BCS. So this formula is exact until order parameter can be considered constant, but it can be considered constant as 0.1 milli-electron volt, 1 milli-electron, so you have to integrate, because this is fluctuating. And you found in this approximation the exact shape. I say that this shape, similar to this jump, but I believe that this is your picture. And you can see how it is similar to this. So I won't say that this is exact solution, and this exact solution will pass here if spacing is very small in comparison with delta. But we can something. We can get this true shape. Very good. So now I want to see what will happen. So I stress this is exact solution. Very rare case when we can write exact solution. Now I want to return to perturbation theory, and from exact to go to perturbation. So I will ask when my corrections are small. Oh, sorry. When my corrections are small. They're small when T minus Tc over Tc remains much less than 1. So I'm in the limits of applicability of Ginzburg-Landau theory. But epsilon should be more than Ginzburg number. What is Ginzburg number? Ginzburg number, this when I showed you when the fluctuation corrections becomes when the smearing is noticeable. So the fluctuation corrections become of the order of the value of jump. So when epsilon is much larger than Ginzburg, so you are here, you can calculate temperature dependence. I already had this temperature dependence in the form of R function, but you do not know asymptotics of R function. Who remembers? I, because I prepared for lecture. So indeed, this is asymptotic of R function. So if you substitute it here, you will see that this one will be cancelled. Exponent will cancel this. And you will have for z, you will have that z is p divided alpha t minus tc over tc. So this is z, so f is minus t log, and this log of p over alpha epsilon. Entropy, the derivative of f. So we have 1 over epsilon. Heat capacity will be derivative. So you will have that the heat capacity here will be 1 over epsilon squared. So critical exponent is 2. So zero-dimensional case, fluctuation correction in the perturbation way. So here is 1 over t minus tc squared. In one-dimensional case, 1 over t minus tc 3 over 2. In two-dimensional case, 1 over t minus tc. In three-dimensional case, square root of t minus tc. But I repeat, we can pretend only at the tail. And the beauty of zero-dimensional that I give you all this figure. Very good. Do you have questions?
Yes.
Yes, please.
Can we associate some critical exponent for this position?
I told you. This is critical exponent.
Okay, I missed it. Probably.
Yes, this is for the heat capacity minus 2.
Okay.
You will see it. I will calculate it for any dimension. Now, next time, I will start to cheat you. So I will do the following. I want to go beyond the immediate vicinity of transition, qualitative evaluation. So beyond the immediate vicinity. So beyond the critical region. So in Ginzburg-Landau region. So far enough from transition, but not very far. So T minus Tc still is much less than Tc, but I do not approach Ginzburg number, I will show it later, gives me where it is forbidden area. I should not enter too close to Tc. Only in zero-dimensional case. And you see what happened. I smeared the jump. Very good. So three-dimensional case. I will say that who ate these things in the lobby? There are some I saw. I have diabetes, but I saw that there are these things with chocolate and some pieces of some grains. And you ate them. So this is.
You ate one.
Sorry?
I saw you. You ate one.
Don't tell to my. So it is why I know. So they are full of granules, but this stick is three-dimensional. So I will say that my three-dimensional superconductor is this stick or
Energy bar, yeah.
energy bar. So this candy bar, and each grain of it is zero-dimensional. So I will say that free energy of one-dimensional specimen is minus T log U over epsilon. So I already use asymptotic. I did not use F function. I use asymptotic behavior, which is good when epsilon is more than Ginsburg. Then I will say how many such pieces I have, the volume of my superconductor divided psi size of my grain, maximal size of my grain, where I still can neglect derivative, in power d, when d is dimensionality of my specimen. So 2 if it is this bar, or 3-dimensional if I will take 10 bars. So free energy, I will say, is just number of such grains multiplied on logarithm. This is not completely true, but is not bad approximation. So I say that free energy of 100 grains is sum of their energies, or multiply of number. Very good. So this formula gives the correct temperature dependence of the free energy not too close to Tc, because I used it not too close, for the specimens of the even dimensionalities. Example, in 3-dimensional case, I will have, look, I calculate a delta C is minus T second derivative free energy over T squared. So this is second derivative. T is Tc, forget about this. But I will reduce the differentiation over T as a differentiation over epsilon. This is Tc, T minus Tc. So psi depends, this is Ginzburg-Landau psi, which is 1 or psi 0 divided square root of epsilon. So I calculate second derivative of this square root, and this they give me 3 over 2, because it was 1 over square root. In the denominator, it goes up. So the second derivative of epsilon 3 over 2, it will be 1 over square root of epsilon. So critical exponent is 1 over 2. For 3-dimensional case, this is a well-known result for fluctuation correction to heat capacity. Excuse me. So it works. Now, I will show you perturbation approach. So this was made for the need. I had solutions for granular, exact solution. I took asymptotic far from Ginzburg. I multiplied number of granules and I got the correct answer. Now let's do this in more formal way. I will say that free energy is A psi squared plus psi 4 plus gradient. Previously, I conserved psi 4 and neglected gradient. And I did not use psi 4 because I took asymptotic, so it was useless. It was in Earth, and I used asymptotic of Earth. But I did not take into account change of psi in space. I told that it is repetition of grades. Now I will say I do not use this model, but I will take into account, I will take into account gradient of psi. I will say that I can expand other parameter in Fourier series, and I will speak instead of psi of R, I will speak about Fourier components. The integral over dv will be performed, and I will have sum over momenta. So I will say that free energy expressed as a function of Fourier transform, Fourier components of other parameter is free Fermi energy of Fermi gas plus sum over wavelength. So I have these Ginzburg-Landau waves. So I sum over all long waves. Long waves means longer than CBCS. I'm close to TC, and only long wavelength fluctuations are important. And I have to perform this. No, I have not. This is free energy. But partition function, I'm interested in partition function. So partition function will be what? Will be integral, functional integral over other parameter, real and complex parts. Okay? Functional integral, I will perform integrating over each Fourier component. So I have huge amount of two-dimensional integrals over complex components, and not sum was here, but sum under exponent is a product out of exponent. So my partition function is a product of 1 million of such integrals of exponent of corresponding modulus of the Fourier component of other parameter. Do you follow me or not? Yes, please.
What is the justification for ignoring the psi?
Sorry?
What is the justification for ignoring the psi to the power 4 term here?
The justification is evident. I do not approach, so I believe that psi is small because I do not approach TC. I'm still in Ginzburg-Landau region. So I'm far, because this psi 4, I accounted for granular with exact integration with R function. Now I define that R function and 1 over epsilon square were the same far from critical region. Now I do the same for three-dimensional case, but I do not touch psi 4 because I say I do not approach TC so close, but I take into account the spatial space fluctuations of other parameters. I cannot do everything. So partition function will give me, so I told you, this is a Ginzburg-Landau functional in momentum space. I substituted in partition function. The exponent of sum is transformed to product of exponents. Integrals are two-dimensional. You see, the problem is that I would not be with this guy. I would not be able to perform this integration because I would not so simply reduce. Psi 4 would not allow me to do this transformation. Now, this integral is trivial. This is just Poissonian integral. And I say that, so you understand how to calculate this integral. It will be, well, yes, please.
Could you repeat this? What is your justification for eliminating the psi 4?
Yes, I repeat that when I spoke about the granular, so this is more or less general formula of magnetic. When I spoke about granular, I told that size of my granular is much less than Ginzburg-Landau. So the change of other parameter in it is negligible. So I believe that other parameter is constant. Which constant I do not know, but constant. So I forgot about gradient, but I carried on forcefully. Then I have succeeded to calculate integral because it was just psi0 constant. So I integrated over all possible constants from 0 to infinity. And I got F function. R function, it differs from 1 over epsilon square from its asymptotic. They allowed me to describe all transition. Now I say that I do not pretend to describe, impossible in this way, describe all transition. It is necessary to use renormalization group, the critical exponents. But far from TC, where fluctuations do not interact, I can do. Far TC, I can forget about this. This guy is responsible for interaction of fluctuations. But in three-dimensional or two-dimensional case, I cannot do this. So I forget about this, justifying that psi is small. Then, nevertheless, instead of it, I take into account for gradient. This gradient, after Fourier transform, gives me k squared. Gradient transforms in k squared. And I calculate these integrals. They will give me a look of modulus psi d psi and 2 pi the integration. So pi will appear here, and it will be integral of d modulus, and here modulus. So this guy will go in denominator, and this logarithm comes because logarithm c. I had product. Log of product is sum of logarithms. So I don't know it works or not to explain so in details mathematics.
We can pass this.
Okay, so in any case, I showed you how I can get in perturbation approach the free energy with this logarithm, and now I calculate the contribution to heat capacity due to fluctuations. So I calculate second derivative of this Ginzburg-Landau contribution to free energy, and this look. Here I had logarithm. I will derive this once over epsilon. So instead of logarithm, I will have this denominator, and then twice I will have sum over epsilon plus chi-square square. And now I can perform this integration instead of sum integration for any dimensionality 3, 2, 1, 0 with different numbers. But you see that critical exponent is 2 minus d over 2. So I did this integration in general form, and you see that d0 epsilon square, d1 3 over 2, d2 1, d3 1 over 2. So I got fluctuation correction for any dimensionality, but only when it grows. Not, I cannot describe all transition, only in 0 dimension. Okay, so what are the values of Ginzburg number? So what means Ginzburg number determines the smearing of transition. For experimentally, this is very important. So why Kamerlingh-Onnes did not say us anything about smearing of transition? Because he worked with three-dimensional specimen, the wire of mercury. It was clean. He did his best to clean it because he believed that he wanted to have this decrease to 0 in clean material. So clean material, and you see that Ginzburg number for clean superconductor is 80 Tc divided epsilon Fermi in power 4. Tc is 10. Fermi energy is 10,000. So this is 10 minus 3. 10 minus 3 in 4 is 10 minus 12. So actually it is 10 minus 14, 10, 10 minus 16 with all numbers. So for traditional, clean three-dimensional superconductors, the smearing of transition is negligible. But it is enough to go to dirty system. This is clean. But in dirty system, three-dimensional bulk. But instead of Tc over epsilon Fermi in power 4, you have only Tc over epsilon Fermi in first power. So this is 10 minus 3 or 10 minus 4. And then 1 over P Fermi L. P Fermi is A. Is A minus 1. So this is a ratio of interatomic distance divided mean free path. And now it depends your alloy how is dirty. So in principle, in disordered materials, you can arrive to 10, which still can be considered as described by this theory. So it will be 10 in power 3, 1000. So it will be 10 minus 6. So from 10 minus 14 to 10 minus 6, just the contaminate in your superconductor. But look what happens in two-dimensional systems. In two-dimensional systems, in clean, but I don't know what means clean two-dimensional superconductor. Because how you will create? If you should have clean some monocrystal, two-dimensional monocrystals. Yeah. So it will be. Sorry?
We heard about this.
Yeah. So TC over epsilon permit 10 minus 3. But if you sputter film, it will be 1.3 P Fermi square LD for two-dimensional P Fermi L. So Ginzburg number can be up to 0.1. And there is practically no room for Ginzburg-Landau theory because T minus TC over TC must be much less than 1 and much more than Ginzburg number. So practically no applicability of Ginzburg-Landau. And even worse in one-dimensional case and zero-dimensional case. Very good. What happens with Ginzburg number as a function along the phase diagram? It is very beautiful. All what I told you was calculated here. But if you analyze fluctuations close to HC2, you will find very interesting things that you will have the same value of Ginzburg number. But when you move along the line HC2 of T, so fluctuations become more important here, and they grow as when temperature, you see, they grow as a square root. Okay, so now I want to discuss do we want to have the break or not?
What is the opinion of the just a question on the previous slide.
Yes.
What do you represent when you do this dashed area? Is that
I mean that here the fluctuations are strong. So they are restricted here, but the effective Ginzburg number changes along this line.
but like the width of the line, like it does mean that if
This is Ginzburg number. Numbers of Ginzburg I gave you here.
Yes, but what you are drawing is like a critical field versus temperature, right? So do you mean that what you will measure will be included within this area?
No, I mean that here you should not come here. You can approach TC, not very close, and your perturbation theory will give you good results. Here there is a critical region. Here's the same story for quantum fluctuations. But if you approach in this way, so the area where your perturbation theory works will be less. Now, fluctuation induced shift of the critical temperature. So, Ginzburg-Landau penetration length follows from the London theory, but London did not use this epsilon. So from Ginzburg-Landau theory, just. So what is supercurrent? How to get it? Supercurrent is a response for vector potential. We know this. And S is the concentration of superconducting carriers. And it can be rewritten in this way. I will average current over fluctuations. How to do this? I will say that current enters in free energy as a product with vector potential. So if I want to get current from free energy and vector potential, I would just calculate the partial derivative. And then I will use fluctuation free energy. So it must be averaged over fluctuations. And this is T d log z over dr. Now I will say what is d log z over dr and where what was z. It was an integral, functional integral over other parameters of the corresponding exponent. Now I have to average this derivative with fluctuation exponent and normalize it. The standard procedure. If you will do this, you will find that G is minus 2e square ma psi tilde. I'm below Tc. So I have the average value of psi corresponding to 2 minima in Landau potential. So this is a standard answer without fluctuations. And this correction came like in heat capacity from fluctuations. So what will be Tc? Without fluctuations, Tc is determined where you do not have more critical current. So when psi becomes 0, psi tilde is proportional to T minus Tc. So T equal to C, superconducting is finished. Now I see that account for fluctuations give me this additional term. So I will define Tc as a temperature, Tc shifted, as a temperature where supercurrent is 0. So I calculate this and I find that in three-dimensional case, the shift of temperature is a square root of Ginzburg number, but three-dimensional Ginzburg number. So it is 10 minus 14 square root 10 minus 7. So fluctuations in clean superconductor shift temperature for 1 million, 1 per million, nothing. But in two-dimensional case, the story is different. First, Ginzburg number is not so small, but the correction now is Ginzburg number log 1 Ginzburg number. So this is famous formula, which I attribute to Ovchinnikov, who got it with wrong number in 73, and then Finkelstein, and we got it in 86, 87. So what happens? What this result says me? I will, yes, please.
Actually, this result also appears in a classic paper of Halperin and Nelson.
When?
It's, I think, in 1979, perhaps. It's a Journal of Low Temperature Physics. I would be happy to show you that.
Ah, okay. Yes, but Ovchinnikov did it in 73.
That may be wrong, but he got the wrong sign.
Yes, he wrote.
Halperin and Nelson got.
Nelson, they got correct sign.
Yeah, of course.
Ah, very. But Ovchinnikov got also a logarithm cube.
Okay, they got a single log.
Yeah. Okay, in any case, thank you. I did not know this. Yeah. So what happens? Happens this, that there is a BCS TC, which comes from this term. Forget about fluctuation. From this term, this is BCS. You account for this term, and TC is shifted down by 2 Ginzburg TC log. So it comes here. And I put that the psi. So in two ways, if I'm interested in the square of other parameter, so if I use just BCS formula, it should be 0 in TC. So first effect is shift of TC and BCS formula. But I say, but I'm interested in psi average over square. So I want to know about concentration of fluctuation Cooper phase. And it is described by this curve. So it goes above. This would be imaginary BCS without fluctuations and only shifted TC. But this is true psi square. So I would say that this is square root of psi modulus not averaged over fluctuations. And then we know, we listened from Christoph, beautiful lecture about BCS, or about BKT, Brzezinski-Tauris Kosterlitz. This is Nelson jump, where the dissociation of vertex-antivertex pairs takes place. And here, the superfluid density fall down as a jump. And this is TBKT. What is interesting is that all what I presented you was now the perturbation approach. So I calculate only, if we speak from the point of view of renormalization group, I did only first step. And then infinite step to come to the fixed point. But I see that the difference between TBKT and this renormalized TC0 only for Ginsburg. So the beauty of this story is that you already, with the first approximation, you exhausted practical renormalization. And you have beautiful matching of two visions of two-dimensional superconductivity. One starting from BCS and seeing how fluctuations destroyed shifting TC down, and other from the vertex-antivertex picture. Yes, please.
But if you think about things in the vortex-antivortex picture, can you, or other way around, can you actually describe or really say this must be TBKT starting out with simple Ginsburg-Landau arguments?
Sorry, I didn't.
If you start out with a Ginsburg-Landau model, can you actually predict TBKT?
Not. TBKT is completely, this is a very simple energetic consideration of the struggle between the kinetic energy and the entropy term.
Just a minute, yeah, there's another question.
Yes, please.
So now with this new definition of TCs, so you said it is when the average value of the supercurrents is 0.
Yes.
And not when the psi squared is 0.
Exactly.
So now let's say you are just above TC, you have no supercurrents, but you still have Cooper pair.
Yes.
So let's say you have transports. So dissipated.
No. Above TC, fluctuations still contribute in conductivity, but in normal. I mean that you have from other side they reduce you they increase you current, they reduce you resistivity, they increase conductivity, because conductivity because look, below TC current is a response on vector potential, and above current is a response on electric field.
So now, once you are above this new TC that we have defined, we can have Cooper pairs which current is proportional to tension.
The Cooper pairs, exactly. The Cooper pairs which move ballistically. So you have normal transport of electrons who moves viscous in viscous way. So current is proportional to derivative of A, dt, dA over dt, so electric field. But you have some current proportional to vector potential. But this current is not continuous. I mean that it is some contribution. This ballistic motion, the characteristic, the scattering time is Ginsburg-Landau time. So they appear, disappear, appear, disappear. So they help you, they increase your conductivity, but this is still not supercurrent. This is a tendency to supercurrent, but fluctuation conductivity is not it is not supercurrent. Okay, now if you are still alive, I will show how to describe in Ginzburg-Landau approach. I will describe the fluctuation transport, because supercurrent was thermodynamics. It is still not transport. Ginzburg-Landau equations are not valid, they're thermodynamic, but exists this extension of Ginzburg-Landau theory, introducing the time-dependent Ginzburg-Landau equation. What means time-dependent Ginzburg-Landau equation? So I want to recall you that I derived for you Ginzburg-Landau equation as the extremum of Ginzburg-Landau function. So I calculated the variational derivative of free Ginzburg-Landau free energy over the first equation was obtained as a functional derivative over size tau. My assumption will be very simple. I have the equilibrium system. Then I deviated a little bit from equilibrium. How it will relax and it will relax to the equilibrium state. And it is naturally to assume that the time derivative of this relaxation should be proportional to that, such value which is zero in equilibrium. In equilibrium, zero is the functional derivative of f over psi. So I will assume that d psi over dt is proportional to df over c. So psi function want to return to the state of thermal equilibrium. This is good idea, but my theory must be gauge invariant. So d over dt appears side by side with the electrostatic potential. So I should not write only deep C over dt. I should write deep C over dt plus 2 phi c. So this proportionality in gauge invariant form, I will rewrite is minus gamma d over dt plus 2 phi applied psi function, the functional derivative. This is model equation. This is done by hands. But in the paper of Garykov and Eliashberg from 1968, they in very formal, difficult way demonstrated that this equation indeed can be obtained microscopically, but with some conditions. That your superconductor is in gapless state. Above TC, no problem, we do not have gap. Below TC, you can have superconductor in gapless regime if you kill gap. Why it is so important, the gapless regime? It is evident. Because gap has a dimensionality of energy. So it gives you some additional scale. Here I say that d over dt, and then I say that this is the, so I do not insert any energy scale besides natural time. But in superconductor below TC, with gap, I have to take into account the special the dynamics with gap. And this is, so there time-dependent Ginsburg is not applicable. You have to kill this gap to have the unique scale. You can, so if you want to describe real dynamics, so follow what I told about our questions. And so where you have this propagator with all gaps in denominator, so do real microscopic theory and you will have these excitations, collective modes in superconductor. You will see these Anderson modes, all this beauty with matrix 4×4. So, and this was done, the collective modes in superconductors are studied, but this is indeed tough stuff. So there are several modes there.
Sorry.
Yeah, please.
Here, P is electrostatic potential, or
Phi is electrostatic potential.
ah, okay.
E is charge of electron.
So like gauge invariance. The argument is the same as like gauging. Is gauging the momentum operator in
yes, exactly.
Okay.
Yes. So plus or minus depends how you define charge of electron, plus E or minus E.
Okay.
Okay, so now I will rewrite this equation in this way, and then how to take into account fluctuations. So now I want to study the role of fluctuations on transport phenomena. So I will say that I will model, so I will distort my system by the random forces, Langevin forces. So your system lives in equilibrium, but every time it is beaten, it goes beyond the equilibrium, then it returns and another force beat it, and this is a model of Langevin forces. What properties obtain these Langevin forces? The correlator of the Langevin forces introduced above must satisfy the fluctuation dissipation theory. This requirement is fulfilled if the Langevin forces are correlated by the Gaussian white noise law. So I will not go in these details. It is necessary to calculate correlator with them, without them, and to see that it is the same. It is possible when correlator of these forces is 2t, real part of gamma, and delta functions. Okay, probably
say something about the temperature dependent of the gamma GL.
Yes, I will.
Okay.
I will calculate it.
Okay.
Yes. So now I will be very formal. I just will rewrite this equation. I will write explicitly. This is just Ginsburg-Lau equation. So I will rewrite it in the form L minus 1 minus phi psi. So what I did, look, I leave in the right hand side only Langevin force. This guy I put here. And I put together d over dt with this guy, and phi I leave apart. So look, this is phi because I will look for the response on phi on electric field. And L minus 1 is gamma d over dt and linear part of Ginsburg-Landau Hamiltonian without the third power term. So this is formal. I just rewrite the equation, nothing else, in the form which is convenient for me. Look now, let's put electric field 0. So it will be equilibrium order parameter, because not equilibrium, it will be order parameter without electric field, but disturbed a little bit. So what I will have that in the absence of electric field, one can rewrite the formal solution of this equation as look, L minus 1 psi. So psi is L applied to Lagrangian force. Now don't think about physics. Don't think only about mathematics. So you still follow me, guys. You can just follow because you have the materials of I presented it, and then I left for Claire also my book in PDF file, so you can download it for you. And I just present the results which were published in the book, in the third chapter of the book. So again, I developed perturbation theory. Phi is 0, no electric field. So phi 0 is this L propagate the operator applied to zeta, the correlator of the Lagrangian forces. This I already told. Let's go down. Paraconductivity. It was calculated by Mazov-Larkin, but in diagrammatic way, in way as I showed you yesterday and today. Here it is very easy to do. Actually, I will say, I will look for the other parameter disturbed by fluctuations in the perturbation way. C1, I'm so formal because I want to get very beautiful formula which can be applied for layered superconductors, for three-dimensional, for granulas, for nanotubes, for everything. So I will speak in some general Hamiltonian. And then I will reduce all to summation over it eigenvalues. So psi is psi 0 plus psi 1. Psi 0 we know. Now I return to my equation and look for this piece here. So I will see that L minus 1, look, this part I will move here. This part I will move here. Phi is a perturbation. So from this piece, psi0 plus psi1, I will forget about this because it will be second order of perturbation. And I will see that L minus 1 applied to psi1 equal this piece. This piece came from here. This piece came from here. And where is zeta? Zeta cancels by L minus 1 psi 0. Okay? So 0 order I cancel. And this is expression for correction. I apply propagator L here, and formally I find that psi1, so the response of my other parameter on the appearance of electric field will be 2E gamma L operator applied to scalar potential. Phi 0 is L operator, the Lagrangian force. So nothing difficult. This is just algebra. Do you follow me still or not? Okay. So all details you will find here. Now I know that current is determined by the quantum mechanical expression. So I will substitute here. This is fluctuation current. So you see psi0 V operator psi1, psi1 V operator psi0. And G is equal sigma E. So to find sigma, I have to extract from here electric field. Electric field is a gradient of scalar potential. So we are close, you understand? We are close. So now I will remember quantum mechanics. and I will say you that V operator is a derivative of coordinate. So this is a commutator of R operator, so coordinate operator with Hamiltonian. I don't want to think. I just do mathematics. So electric field I will present as the so scalar potential is electric field multiplied R, as it must be, with exponent minus E omega t. So I take into account R and T dependencies. So R, from this relation, I will, after some algebra, which we can discuss, okay, we cannot already, but you can find here. So I will express matrix elements of R operator from here. You understand? V, R. So formally R is V divided H. H has its the eigenvalues. So this comes from this quantum mechanical relation. And finally, after some algebra, I find that tensor of fluctuation conductivity, which is valid. By the way, you asked me about, who asked me about the frequency dependence. You asked me about. So look, this is expression for paraconductivity, which is valid close to TC, so T minus TC, magnetic field and frequency. So this is very general. It is why I tortured you with all this, the matrix algebra. So this is very general expression. I got paraconductivity for temperature in Ginzburg-Milnau region, for any magnetic field, for any frequency, and for any spectrum. I mean that all information about your superconductor is here in the eigenvalues. So two-dimensional, please write two-dimensional Hamiltonian, three-dimensional, three. What do you want? And you want Hall effect, you can have the sigma xy. You want conductivity, sigma xx. You want perpendicular conductivity in layered superconductor, sigma zz. If you want the nanotubes, write the geometry, the spectrum for a nanotube. It's a very general expression. Now, the isotropic case, the simplest, and paraconductivity. So longitudinal, yes, please.
So, sorry for interrupting. To the previous formula, the formula, it really reminds Kubo formula.
This is a Kubo in some sense. I found you linear response.
Okay, but this was done with Landau-Ginzburg formalism.
It is time-dependent Ginzburg-Landau formalism and a little bit of perturbation theory.
Okay, so in principle, it is literally.
It is linear response. Okay. You see, this is linear response.
Okay. Yeah.
But here also the real and imaginary parts. You understand? Here, because gamma, here you see this E. So you have also imaginary part. Okay, so now isotropic case. So for longitudinal conductivity, I will have formulae simplified, strongly simplified. And I say that epsilon of P, we know it is T minus Tc plus Q square over 2m. So you can easily calculate derivative. It will be 2 alpha Tc psi square P. You substitute it here, and you get already with all correct coefficients paraconductivity in 1-dimensional, in 2-dimensional, in 3-dimensional. And in contrast, what I showed you before yesterday by hand waving, when I got you this way, as Lamaza-Larkin formula, but without coefficient E square over 16D. And here you have all correct coefficients. So this is much simpler than to calculate diagrams to get the same results. So these results reproduce the microscopic calculation, diagrammatic calculation of paraconductivity of solid. And we can get much more with this formula. I mean, we can get whole. Then in the book you will find I can in the same way calculate your corrections to Nernst effect, to thermoelectricity, to heat conductivity. All this is possible to do in the same operator way. So there are these formulas. Very good. Now, diagrammatic description. This is what we discussed with you today and yesterday. Sorry?
During the Q&A.
Yes, during Q&A, we described, and now very good that we discussed because you understand better these pictures. And you understand we calculated with you yesterday this L polarization operator. We got this form. We remember about green function in Matsubara representation of fermions, and we got the propagator analytically continued close to TC.
Sorry, Andrew, can I come back to the previous thing?
Yes.
So paraconductivity is again finite lifetime, right?
Sorry?
It's paraconductivity is finite lifetime. So it's the maps of Larkin, right? Finite lifetime of
yes. Lifetime you use as the in hand waving it was used as a scattering time because to be scattered on two die is the same. But the answers here they give real change in conductivity.
Yes, but where do you see? So where was the ingredient of the? So it's the Langevin forces that give you the scattering. What was it?
They modeled me interaction with bus, with condensate, and you got the traces of this Ginzburg-Landau time are here. Sorry. So they are here. The square root of epsilon is the, or this 1 over epsilon is tau Ginzburg-Landau. But it comes completely, we did actually, I did not use Drude formula. I did not use Drude formula, I used the linear response theory. So I looked for the response of the system on applied electric field. Okay, so this I will not explain, we already discussed it 3 hours. So I want only to say you formally again, I want to explain how Larkin and Mackey invented their diagrams. Why these diagrams? And I repeat that at the example of thermodynamics, the contribution of fluctuations in thermodynamic potential is this one. If I want to calculate entropy, first derivative, so I do this as I told, I do this. So I break one green function for 2 with some vertex. So I will have one tail here, one tail here. Then I will open this propagator because propagator is sum of bubbles. I will open one bubble and put derivative there and from other side. So finally I will have 4 the same diagrams because this is reduced to this. Just remembering that this piece and this is one bubble. So I collect them again in wavy line. And so this is the first derivative. And then if I want to calculate second derivative heat capacity, so I will derive again, and again, but 2 tails will finally I will have 4 diagrams. This, and this. So with heat capacity is clear how to do. With transport it is more sophisticated, but topology is the same. So Aslamazov and Larkin decided that this diagram is most important. Why? Because the propagator wavy line is singular. Omega 0 Q0, which is 1 over T minus Tc. And in this diagram, you have two propagators. So it is more important than other. Indeed, these diagrams, those were calculated by us with Larkin, Joffe, and Yulu only in 92, and we demonstrate that it is indeed the important only in special cases why Aslamazov, Larkin, and Maki Thompson are suppressed. But Larkin and Aslamazov missed this diagram because it seems that it is not so singular, one propagator. But here there are dirty vertices. So it sums of these diagrams with impurities, these Cooperons. And they give you an anomalous Maki term, which is not less important than Aslamazov-Larkin, even larger logarithm. And Maki skipped this diagram because he did not do this procedure. He invented, I know how. He had paper of 1964, how to take into account below TC in gapless regime with small gaps. So he just connected these gaps and got his diagram. He did not do what I did because I did all topological possibilities. So it was nice that in the same 68 were published two important papers, seminal papers, one of Aslamazov-Larkin with this result. This is Maki Thompson. As I told you, it was here the calculation was sophisticated because it is necessary to do analytical continuation, non-trivial, the poles, etc. But it was done. Maki obtained his result, but he did not know how to cut this logarithm. It is Dick Thompson who proposed to cut it in the pair breaking mechanism. Okay, so now fluctuoscopy, I'm finishing. So fluctuoscopy, arbitrary temperatures and fields. So till now is close to TC. And it is enough to study fluctuations more than 50 years. So it was time in years 2010, it was necessary to give tool to experimentalists to use all this, not only for physical beauty, but to use to characterize the new superconductors. Namely, yes. So this is typical behavior of resistance as a function of temperature. And what identify with critical temperature Camerlin-Onnes, it is clear. But how to define here critical temperature? Half of transition, 0.9, 0.1, inflation point, who knows? So we believe that we cannot identify it at all. The critical temperature should be defined as a fitting parameter. So to take experimental curve, to take all corrections, so weak localization, the spin orbit, anti-localization, depends on you have, fluctuations, and fit your data. And extract TC side by side with tau phi, with the elastic scattering time, the three parameters, to feed this data and to get TC. And for this reason, it was necessary. So what is if you want to do this close to TC, situation is simple. If you want to do this also in magnetic field, so it is necessary. This is general expression, which we got with the Vinokur and Glatz in 2011. And it describes all phase diagram. What was found? That where this is a superconducting diagram, magnetic field, temperature. You see that there is a line below which fluctuation correction, which is a sum of all Aslamazov, Larkin, Maki, Thompson, DOS, is positive. but DOS contribution is negative, and we understand why DOS is negative. Because Aslamazov-Larkin is additional channel of charge transfer. Mackey-Thompson also. But DOS, it is a lack of electrons on their working places. So it is negative contribution with respect to DOS, to the formula. Because you put not complete number of electrons to Drude. So this is a lack, but this is only logarithmic. So it is less singular. But when you go far from transition, this logarithm becomes important. So you see that here total corrections is positive, but here it becomes negative. And in the regime of quantum fluctuations, it is completely negative. So all this is described by this formula, and I will show you how. So for instance, the experiments of Baturina and company on the niobium nitride. They first in 2011 used this formula with Glatz to fit their data, including, as I told, VUC increase, etc. So finally, they determined critical temperature and the determination of TC as a temperature where RT drops to 0.9 or 0.5 significantly overestimates TC. So according to the extraction of TC from fitting shows you that TC is low enough. All this beauty happens above TC. Then this is electric field control of fluctuations in two-dimensional superconductor. This is still unpublished result with a group of Andrea Caviglia. They used the field-controlled superconductivity, and they changed critical temperature in two-dimensional electron system, applying voltage. So they change concentration of carriers, applying voltage. And you see that the these are dependencies of R as a function of T. You see how a change in voltage shift you transition. And here it is beautiful that they invited us to participate in this work before they tried to fit their data just with Aslamazov-Larkin. And you see that fitting was not very good. And then here you see the fitting, almost perfect fitting with a complete formula. And the conclusion that main contribution here is Mackey-Thompson. So what indeed determines the shape of transition. Then I will finish with probably, this is our very fresh paper. It will appear these days in PRL. With proposal how to observe formation of a precursive vertex lattice still in normal phase. So we are at here. One moment, where we are. No, we are not here. Where we are? No, where is my phase diagram? No, it is not here. It was last.
You turn to the beginning. You're in the beginning of the.
Oh, the first lecture.
No, this is. You going?
Yes. No, I mean. Okay. I once maybe here. Yes. Yes, I won't say that I want to be here. So at HC2, and I approach it at zero temperature. So purely quantum conditions. And I won't say that here would be.
So you approach HC2
from above
magnetic field.
Yes, I come to HC2 from above at zero temperature. Yes, please.
Can I ask a question about this? How to read this phase diagram?
if I remember the data from Tatiana Baturina, for
Yes.
example, she sees when she lowers temperature, then at zero magnetic field, then the resistance, of course, yeah. When you talk about
No, but I want now
I think I
to
understand.
approach here.
No, I don't understand it actually. Sorry, it's late. She sees that the corrections first turn the
She's here.
up, yes, and then down, but she,
But up and down, she took into account the weak localization. Weak localization brings you up.
oh, this is not in this picture.
No, this is only fluctuations.
Okay.
So the question is, so I cited from the very beginning Leibniz, natura non facit saltus. So how we should imagine formation of abricosal letters. I take niobium film. I approach HC2 is 0.2 Tesla. I am at 0.201 normal metal, all is quiet. I am at 0.19 suck, and I have abricosal lattice. How you imagine that it appears from nothing? Evident is that it should show up itself still in normal phase. In what way? We know what happened above this. Two electrons try to live together. They live, transport, they carry current, contribute to the heat capacity, do what they want. And you imagine them at the violin. And in this violin, there are waves of different wavelengths. Psi k, you saw. Not very short, because the theory is valid until these waves psi is larger than psi BCS. But then you have, if not violin, take a contrabass. So, and they live there. Beautiful Rayleigh-Jeans picture. But when you move along this line, new parameter appears. This is magnetic length for Cooper pairs. When magnetic field is small, magnetic length is 1 over square root h, it is large. Forget about this. But at some moment, it becomes comparable with Ginzburg-Landau. And magnetic fields start to break your waves and transform them in vortices. It happens somewhere here, but I want to be here, where definitely the picture is not wave at all. Cooper pairs is formed one Cooper pair, and it must immediately start to rotate. How it will rotate? Exactly like Cooper pairs rotate in abricosal vortices. So size of this rotation will be psi BCS.
But you're in strong magnetic field, so wouldn't you naively assume that you have probably some kind of Landau
yes,
quantization?
Of course,
of the
yes.
of the electrons?
Exactly, it will be Landau quantization, and all the microscopic consideration is performed in the Landau. So all formal parties, this. I speak now qualitatively. And qualitatively I say that if Cooper pair is formed, so this immediately starts to rotate. And period of rotation is the same as in vortex. This is delta minus 1. It is superconducting delta minus 1. I can show this without diagram. Just as I did at the beginning of lecture 2 days ago. So tau 1 fluctuations is delta, but tau quantum fluctuations, if I evaluate it from Heisenberg inequality, will be delta minus 1 divided h minus hc2, h divided hc2. H close to hc2. So h minus hc2 divided hc2 is 0.01. and period of rotation, delta minus 1. So this fluctuation Cooper pair should live 100 rotations. So this means that it will participate in many such rotations. And size of this domain will be from Einstein-Smoltuchowski square root of tau quantum fluctuation. So it will be exceed the by Barton-Cooper-Sheffer divided square root h minus hc2 over hc2. So it will be 10 psi. So 10 vertices will be involved, 100, 10 in length. And this will be piece of future precursive lattice. But this piece will appear and disappear, Take good camera, put short exposition, and you will see it. Put exposition 100 times longer and you will not see it. All will be smeared out. So we do not have such camera. You cannot do STM because it takes time. So how to see this? You can calculate contribution to direct current. Yes, it will give you negative contribution, dose to this, but not dose, but some kind of Mackie-Thompson, does not matter. But it will give you only logarithmic dependence. So we propose in this paper to test it by the high frequency measurements, the impedance. So appearance of imaginary part of impedance on the film in the fluctuation regime of quantum fluctuation, so above HC2. And our finding is, so you, if you speak about the normal metal, so you understand this real part resists up to omega tau of the order of 1, and imaginary part, this is true there. So all happens in the scale omega of the order of tau minus 1. In dirty metal, this is very high frequencies. This is true default. In low temperature superconductor without magnetic field, at 0 temperature, this is all the because of Garkov-Halatnikov paper, where they demonstrated that you have a gap and imaginary part of sigma appears only starting from 2 delta. So you can expect something in imaginary part of impedance only at frequencies of the order of 2 of delta. What we found that if we calculate all these diagrams for frequency, non-zero frequency, that non-zero magnetic field close to HC2, and low temperatures, so we will find that there is a DC contribution and then the real part and imaginary part. And this imaginary part, what is important, shows up itself at the delta multiplied H minus HC2 divided HC2. So close to HC2, the frequency range when you will detect growth of impedance will be 2 orders less than delta. So much before, and it will be the characteristic signature. So it is possible studying the superconducting field of, let's say, niobium, slightly above HC2, put it in the resonator and measure it.
But the frequency can be terahertz.
The frequency must be 100 megahertz. Yes. Yes.
You said, but delta should give you about a million volts.
This is a CMS of this situation. that for niobium, I speak about niobium, TC is 9.
Delta is about 1.5.
So I would say that these are several gigahertz, and you multiplied it on the 1%, so it will be much less. So this is not so high. We also believed in terahertz, but for niobium, it is in the scale of 1 gigahertz. So this is possible to measure, and it will be the direct signature of formation of these clusters, that they start to absorb energy.
Sorry.
Yes?
Maybe naive question, but why not measuring just whole conductivity?
Whole?
Yes.
Yes, you can measure whole conductivity. Yes.
Yeah, in this case, if I understand the picture correctly, just slightly above HC2, we still have the Cooper pair, which can start to form.
No, I understand that these Cooper pairs will move. I cannot say you now which singularity, because the struggle is you can measure direct current, but it will be low. Probably you are right. Maybe Hall will give you some, because you should remember that all these corrections are proportional to Ginzburg number, so they are small. So to demonstrate convincingly the effect, it would be nice to see something very different from normal. And here the dependencies are not logarithmic, but you see they're singular.
What would happen? What would be the signature as you cross HC2? So you say above HC2, you're gonna have some kind of a what?
Yeah, you can this growth with HC2. You can this growth of the imaginary part of conductivity. So this is dependence on frequency with maximum, and then you see how you fix frequency and how your corrections will grow with approaching of H tilde is related relative to H minus H2 divided by H2. So you have singular contribution.
These are corrections to Metis-Bardeen.
This is correction to impedance.
Okay, so Metis-Bardeen.
Sorry.
So Metis-Bardeen is BCS.
Metis-Bardeen is BCS.
And then this.
This happens much before.
To take into account fluctuation.
Yes, it happens much before. So still, in superconducting state would be still gap. You will have 0 in sigma. And here you in the normal phase you should have 0 in. But due to these clusters, you will have contribution at early stage of volume.
Andre?
Yes.
Is there any experimental data that this occurs at 100 megahertz?
We still do not have experimental.
So we have experimental data which might be related.
You approach close to HC2.
Yes, we have experiments. So we repeated some measurements which were done in the 1970s.
Yes.
That there is a very strange effect which people in those times call the reverse Josephson effect. That if you shine RF, sometimes superconducting fields give a DC voltage. So this had been long forgotten, but there's some literature in the 1970s. So 2 months back, we took niobium fields,
yes,
8 Kelvin DC,
yes,
around 10 millikelvin temperatures, and we applied magnetic field HC2, and we found DC voltage peaks with RF radiation between 100 megahertz and 1.5 gigahertz.
It is what we suppose
it must be. Disappears beyond 1.5 gigahertz. It disappears below 100 megahertz. And we have a huge amount of data.
Thank you very much.
Not to hurry down.
So let's discuss this.
It starts at 100 megahertz. So
fantastic, because it is actually the range which we predict.
Yeah, so and it is.
Thank you very much. Let's contact about this, and it would be great because this publication will be these days. And we do not have any experimental.
So this is a theoretical paper, right?
Yeah.
Oh, excellent.
Thank you very much. Because I spoke with Rodichev 3 months ago, and he gave me the hints how it is possible to measure, but still there is no.
So I think this is a recall-Josephson effect which has long been forgotten after the 90s.
This is quantum noise.
Yeah, but in the tunneling, not in the transport.
Sorry?
Noise in the tunneling measurement, not in transport.
I did not say about tunneling. About tunneling, so I wanted just to finish my lecture. Sorry. So other applications of the fluctuation fluctuoscopy. The 26 years ago was a great noise about the giant Nernst effect in high temperature superconductors. So the Nernst in superconductor, you remember what is Nernst effect? You apply magnetic field in this direction, you apply gradient, this 18,000. You apply current in this direction and you have gradient of temperature in the third direction. Or vice versa, you apply magnetic field, gradient of temperature, and appear the voltage if you have open circuit. So what was found that the Nernst effect in pseudo gap of superconductors was 500 times more than a normal phase. And it was then how the Nernst effect is realized in superconductor due to motion of vertices. Vertices are normal; they have normal force, so they during this, if they're not pinned, so they carry entropy, and this means the Nernst effect. So on, who discovered this experimentally, he speculated that in superconducting, in pseudo-gap phase, exists not only pseudo-gap, but also pseudo-vertices. Who are these pseudo-vertices? Only words. But now we start to understand that pseudo-vertices can be fluctuation Cooper pairs because they rotate in strong field. So they can be considered as vertices above line HC2 of T. So we calculated the Nernst, this was 1999. In 2006, Kamran Benya with his group, so Alexander Pure and Obin, they demonstrated that the same giant, even much more giant Nernst effect was observed in the niobium silicium with critical temperature 0.38 Kelvin. So definitely normal and the conventional superconductor. But the effect was 2000. And we, with Serbin, Galitsky, and Skvortsov, calculated this. So these are results of Benya group. And actually, we explain this very simple. So let's do the following. I apply magnetic field and electric field. What happens? We remember from the university physics that if I have motion of charged particle in crossed electric magnetic field, appears the drift velocity. Drift velocity. So no. Yes. So it should appear current due to the drift velocity. But I have broken circuit. So this current cannot flow. So someone has to stop it. Who will stop it? I say that here should be constant electrochemical potential. Electrochemical potential is mu plus iffy. So this means that to stop, to create countercurrent, to satisfy that there is no current in broken, for me, it is enough to create the gradient of chemical potential, which depends on temperature. So, due to this simple consideration, I see that I can satisfy absence of current if the difference of temperature appears. So, this is the Nernst effect. So, with broken circuit. So, I will say that I can, from these simple considerations, demonstrate that Nernst coefficient is proportional to d mu over dt. The temperature derivative of chemical potential. Look, let's suppose that this slab is normal metal. What I can expect? Mu will be mu0, very large value, epsilon Fermi, minus t square derivative temperature. In the denominator, mu. So the chemical potential is large, but derivative is small. It will be t over epsilon Fermi. It will be 10 minus 4. So the Nernst effect in normal metal is small. Now let's, this is answer. It is small, t over mu. Now let's speak about chemical potential of Cooper pairs. In superconducting state, it is 0. But above Tc, there is no boson condensation. You have these composed bosons, but they not condensed. So how to calculate mu? Mu is dF over dN. Free energy, we calculate it with you now. It is epsilon log 1 over epsilon. Number of particles is just log 1 over epsilon. Mu is dF over dN. dF over some parameter, does not matter which one. And you will see that mu is Tc minus T. It is negative, as it must be. It is very small, it turns 0 in the point of transition, but derivative is minus 1 instead of 10 minus 4. So, due to fluctuation Cooper pairs, in this geometry, you have to expect the Nernst effect 1,000 times more than in normal phase. It is what was observed by Bain. Where is fluctuoscopy? This is beautiful.
What about from the normal part? Doesn't it?
Forget about them.
Well, why are you allowed to forget about them?
Because it is T over mu. You have normal part and some Cooper pairs.
Because it's really small, so now
it is very small, yes. And this gives you a huge contribution. So we calculated again the same procedure of diagram, blah, 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 for any. Now, why it was important? Because it was difficult. I explained you what happens here. But the experimentals measured these beautiful curves. And it was very difficult to explain the motion of this maximum. And it remained for another 15 years without explanation. And in 2020, probably, we with Alexander Pourret and with Glatz analyzed these curves with a fluctuoscopy and have succeeded to do these beautiful curves, which explain experiment very well. And I have 5 minutes, and I will not stop. I will tell you about the role of fluctuations on everyone is exhausted period, but it is not sportive to stop now. To say you that I speak without the break, so 5 minutes more. I will tell you about the pseudogap, fluctuation pseudogap. So look, the fact that you form Cooper pairs means that you steal them electrons for it. The material you steal from Fermi level. So at the Fermi level should form some pro-image precursor effect for gap. Indeed, it was calculated 50 years ago by Abraham Martaredin, and they found that very, very steep dip here in density of states in the scale T minus TC.
These are the fluctuations. What are they?
No, this is density of electron states. So this is normal matter constant. And the fact that you take electrons form your gap. And this gap is very profound, but the integral, this surface is equal to this one. So there is some rule. You cannot create electrons. You cannot eliminate them. You just redistribute. So this was the formula obtained by this group. What is important? Important that the integral of it must be zero. And this varies due to this some rule. This strong singularity, how you can observe, here there are experiments, how you can observe density of states.
Geoffrey's measurement from 1960, right?
What?
It's a tunneling measurement.
Tunneling measurements, very good, tunneling measurements. And what you measure by tunneling?
Single electron density of
Sorry?
single electron density of sphere.
Integral mu1 epsilon mu2 epsilon plus PV n of epsilon plus PV minus n epsilon. Sigma is dE over dV. I have tip of tunneling and something what I studied. So I will call this guy, this EV will be constant. So tip. And this I studied. So if I will derive only this. And dN over dV, the energy is 1 over cosine hyperbolic square. So I will say that this is integral mu of epsilon dE cosine hyperbolic square E plus EV divided to fraction. Very good. Now I will I will do the following. I will say that the integral of mu of epsilon from 0 to infinity, the epsilon is equal to 0. I will extract from here this formula. I will have that sigma is integral from 0 to infinity, mu from epsilon, 1 minus 1 over cosine hyperbolic square d epsilon. 1 minus cosine square will give me cosine square minus 1. What is sine square? Sine square divided cosine square is tan hyperbolical square. Tan hyperbolic square E V plus epsilon 2. So if mu changes slowly, so much in the scale much larger than temperature, then forget about this. It will give you practically, because this is such function, tan square. 1, 1, and here 0. But this dip does not disturb you. actually you measure density of states. But if density of states, like here, change in very narrow, so namely this part is suppressed by this time. And I will have something. But this something will be not in the scale t minus tc, but in scale t, and not 1 over t minus tc squared, but logarithm. So this, the sum rule, makes me observable. This is my imaginations, these calculations. But when you measure, you will measure this above tc. So you will measure some kind of pseudo gap due to fluctuations. And scale will be real gap, because this point is pi t. Pi t, and delta is 1 over 76 t. So this resembles you gap, but not profound to 0. It is logarithmic. It grows when you close to tc. And this pseudo gap is due to fluctuation. So, okay, here I explain the mechanism of formation of this gap. Maybe I will not so because too sophisticated. Yes, please.
Why can the argument about the shape of the measured gap not be made for any gap? Is it because this gap is really small and the normal superconductor gap is fine, or what's the difference
No,
here?
this is not small because this is TC. This gap is TC. This value is EV equal pi t. So if you identify this with gap, so it seems it is almost delta. It is a little bit more than delta. But of course, this magnitude is small because always there is a Ginzburg number.
Maybe I should rephrase my question. You just argued that we measure a gap that does not touch, that looks like not a full gap.
Yes.
But indeed there is a full gap.
What?
Whilst in reality there is a full gap, we can just not see it in the measurement.
No.
Was that not a line of
I won't say that the gap in that you should not identify what you see in tunneling with the gap in density of states.
Yes, okay, this I understood.
Because the density of states due to fluctuations change very sharp, very fast in the scale t minus tc. And formula which identify to you the dip in tunneling conductivity with density of states valid only, okay, I will show. So I want to finish this, okay, does not need, I want just to show recommended books if you are interested. So all about fluctuations, which I told there are here, and Claire have this, it will be hidden in our site. This is the book which I hope will appear. So all my these excursus to history of superconductivity will be here in the next months. This is my old book, The Wonders of Physics. It's the 4th edition about the physics around us and physics in kitchen, etc. This is Le Kaléidoscope de la Physique in French, and this is its translation from French to English. So maybe I will finish here, and if you want to discuss, because I need the black.
I would like to.
So thank you very much for your attention, and I
since it's 7, that whoever wants to stay behind and ask questions is welcome to stay for as long as our esteemed.
No, I have 5 minutes.
Is willing to stay, which means 5 minutes. Let's open the floor to everyone.
Yes. If you have questions, I will answer. But I think that people are already exhausted now. Okay. I want to maybe to, so can we,
Yes, yes, so represent US. Yes. That's it.
because this is important question for people who measure tunneling. So current, so do you agree with this formula? Sigma tunneling voltage integral minus infinity, mu in the study sample of energy of d energy divided cosine hyperbolic square energy plus EV divided in temperature. This formula is clear. Yeah.
Yeah, if we assume that the material with which we measure is boring, then yes. Of course.
Yes.
Yeah.
Then you say my u is a slow function.
Slow in what?
Slow, I mean that characteristic energy is much more than temperature where the changes happen.
So energy changes with temperature slowly.
So I won't say is that it changes in so Fermi energy. So it changes in the scale Fermi energy. Fermi energy 10,000 Kelvin, and you measure at 1 Kelvin. So the changes of density of states happens in electron volts, and here is 100 microvolts. So you can say that this is a slow function, or you study the effect of the impurities. So changes will happen in 1 over tau. So nu is slow function. In this case, I won't say that what is 1 over cosine. 1 over cosine is this function, which width of it is temperature. So if I apply it on nu, so it will filter me.
Yes.
So it will delta function.
Yes,
And it will give delta or a nu of EV minus 3. So study tunneling conductivity, you study energy dependence of density of states, okay? But important assumption is the slowness of nu. Imagine now that nu is doing this. So you cannot consider this as delta function. But you have to respect that the integral from 0 to infinity to this delta nu is 0. And then the story repeats. I will extract 0, and it will be integral 1 minus 1 over cosine squared e plus ev to t delta nu dE. And this will be sigma tunneling. This will be
delta nu is a variation from.
This is a fluctuation. I speak about this fluctuation from constant. So this is tan hyperbolic square EV plus E divided by T. And then you have to calculate this convolution.
Yes.
And result is that these beauties of density of states in the scale T minus Tc will be in the limit where tan is suppressed. So you will work with states. And in result, all this fluctuation due to all this singularity span of the t minus tc square will be cancelled out. And you will get only logarithm tc t minus tc as an amplitude. But then you will have beautiful real part of second derivative 1/2 minus EV divided 4. And this will give you log Tc t minus Tc, the amplitude, and this will be EV P Tc. And it resembles much the BCS. But this is false. But this is not reflection of density of states, because in BCS you have real this gap, real gap, and corresponding voltage current characteristic. Here I would say that this is a false, this pseudo gap. This is reflection of change density of states, but not so singular that in my head. And because of this, some rule changed me two things. Less singular and carrier of function is different. Not t minus tc, but t. Okay, guys, I'm exhausted. For your questions.
Tunneling because I'm doing things further.
Yes. Please send the
online of the report.
Yes, but we have very good. Send it to me now. I mean, no, because from 9 to the morning without stops.
Try.